Well, in this video, we're going to start chapter 2. And chapter 2 is going to cover limits of functions, and we'll do some comparisons to the limits of sequences. We'll find all the, there are very many corresponding theorems that are analogous to each other. We'll look at the algebra of limits and the limits of monotone functions. That's all of chapter 2. 2.1, we're going to define the limit of a function, and you've probably seen limits quite a bit in calculus, but we'll look at it a little bit differently today when we actually prove that a particular limit exists for a function at a particular value of x. And this is not the official definition, but informally, the limit of a function f of x as x approaches some real number, this real number doesn't even need to be in the domain of x, is capital L, the real number capital L, if the function gets close to L as x gets close to a. And I always like to think of f of x as being the height of the function if you're looking at the graph. So as x moving left to right gets close to a, the height of the function is going to get close to capital L. And this is just a simple example by picture. Here we have some function that's graphed, and I chose some particular value a on the x-axis where the function's not even defined. You can see there's a little hole in the graph there. So f of a does not exist. But by my picture, it looks pretty clear that the limit, in other words, as x gets close to a, from either the left or from the right, the height of the function is going to get very close to L. I'll just put a little mark there where A is. And in the definition, we'll see this in the next video, the number A where we're taking the limit, it has to be an accumulation point of the domain. It doesn't have to be in the domain, but there has to be every interval that surrounds A has to contain an infinite number of points of the domain, or numbers of the domain. That's just the definition of an accumulation point. And one more thing, just to kind of prepare us for this definition. You remember in the limit of a sequence, we always had an epsilon greater than 0, and we had to come up with a capital N. Well, we're still going to have an epsilon greater than 0, and that's going to represent kind of a window around the limit. We're going to have an L plus epsilon, and we're going to have an L minus epsilon, something like that. So this distance would be epsilon. It's greater than 0. That distance is epsilon. We will need to find a delta. Think of that as maybe a little window, an epsilon window around A. That's going to be, let me do an example here. I have to make it a little bit smaller than that one. So we're going to get A plus or minus